last lecture in this semester. So today we plan to close chapter 2. We will summarize the basic law by the integral form and maybe relate something related to the previous we talked about differential equation. Then we will go into the chapter 3. Basically, we will use the basic law to talk about the Cauchy flow. This is very classical flow. So this is the plan for today. Okay. continue last week. We talked about the Reynolds transpose theory. So last week we spent some time to talk about Reynolds transpose theory. So right now we just use the RTT to talk about that concept. So we don't need to draw the figure something. Okay. So sometimes specific term or technique term can give us a lot of convenience. We can reduce a lot of explanation. So for the control variant or integral model, you can see compared to the differential material derivation, they are consistent. So partial T, this is the differential inside the control variant. And the convection is related to the in and out from the control surface. So if we take a look, the control variant, this represents total mass. And this represents in and out flow rate. Then this B can be any extensive property. Okay? So what difference between the extensive property and the intensive property?
Temperature. Temperature is intensive.
The what?
Temperature.
Pressure.
Temperature. When
Temperature.
temperature.
Pressure also. So what the difference between the extensive property?
They don't relate to the mass.
Yeah, I think mass is most important. Okay? And if we consider the extensive property, for example, use the mass conservation. That means you maybe have a large system or small system, but if you divide by the mass, usually this is related to the specific property. In the thermodynamics, usually you will have this property. For example, internal energy and maybe enthalpy. Because unit mass, how much they represent, then that will be related to the specific property. So for the mass conservation, this specific property will become to a 1. And if we substitute into here, you can rewrite this equation. You substitute to the 1. So you can see this is total mass in the control variant. This, just like we mentioned, this is the mass in and out the control surface. So that's in and out into the control variant. Then for this equation, in your engineering mathematics, if you have this dot into the control surface, this must be closed surface. In this closed surface, you can use this Gaussian theory because the in and out is closed control surface. That means that's control variant. This closed control variant, their flux change is related to in and out of this control surface. Okay, so you must remember this is the closed circle. In your engineering mathematics, they talk about closed circle. Closed circle, that means a closed system. Closed system is the line is closed, but for the physical, you can in and out, so it's not a closed system. Okay, physical closed system is you don't have a mass in and you don't have a mass out. But for the mathematics, this is defined by the circular. Okay, so for this diverge, you can use this flux to represent. So you can substitute this into here. So you can see there will be plus 2 control value. So for this control value, you can rewrite this equation. So this equation is same as the differential equation we use in mass conservation. This one, we can change, because the differential by the time for the control value. But in the differential, because different time, and also we still have a space, so this dt, we will use the partial t, because they also have a space parameter. It's not only the time parameter. Okay? Okay. Okay, so for the conservation of linear momentum, this extensive property we can show in like this. Then you can see this specific property is also the intensive property. In some cases, it's like this. So for the momentum, this force basically is a momentum change. So in the control button, we can write down like this way. Control button and the control surface. Usually, some students will confuse about this velocity in the control surface. Basically, these two velocity is different. Because for the parenthesis, this part is considered the mass in and out into the control surface. This velocity corresponds to the force direction. For example, x direction. X direction is only considered the u component, similar to this. But in the parenthesis, still the mass in and out to the control surface. Okay, so although here we present like this way, if you write down in the x, y, z direction, this will correspond to the u, v, w, correspond to this x, y, z direction of a force. Okay, so this is a common, it's very common confusion for the student. Similar to the differential equation as well. Differential equation, in the momentum equation, we also have some convection term, then have some the force term. Your acceleration change is only related to the force. X direction acceleration only related to the x direction force. But the mass is related to the control surface and the control button. Okay, you can compare this with the differential equation. One is for the mass, one is for the force. Okay, so for this equation, we are talking about the inertial control button. This is true for the stationary and constant speed. If you have an acceleration control button, you need to consider the external force, additional force. Okay? Anyone have an idea about what kind of a case is the acceleration control button? If you take a bus, the bus from the stationary, then they start to move in. Usually you will feel the force. That's very standard acceleration control button. Or if you are unlucky in the elevator, then that line is broken, then you will feel sometimes there is no gravity force because you fall down. is with the same gravity acceleration. So during that time, you will not feel any force because you are in some acceleration coordinate. But suddenly, if they stop, you will in very strong acceleration control pattern because they start from some velocity to 0. So that will be very large of an acceleration control pattern. So you will feel a lot of force in your body. So in this case, how can you do? Pray. No, I think this is usually a very unlucky situation, but stops that momentum, that's instant. Basically, you will feel certain direction of a force because you have suddenly acceleration. So in that moment, if you jump in the inverse direction, I think it's a jump. Okay, then you can make that force a little bit smaller. Okay, so I think that's certain of just from the physics to talk about this kind of a situation. It's just like in the bus, if there's suddenly acceleration, you will try to use some force to balance your body. If you don't use the force, you maybe just fall in another direction. But if you try to use some force in inverse direction, you will still stand up. So similar situation, that is a vertical acceleration coordinate. Okay? Okay, and other last term is you can see the mechanical momentum equation. This force is also represent the mechanical energy component in the energy equation. In the energy equation, we have a pressure. Before we talk about the pressure, we come to the useful mechanical energy. Then also here have a viscosity force for the surface force. Viscosity force, we reduce this useful energy. And also the body force, about the gravity force. So gravity force in the momentum equation, there will contribution some kind of potential energy in the energy equation. So from momentum equation, you can see the mechanical energy component, their contribution. So if there is no any temperature difference, then energy equation will become to what kind of equation? We mentioned before. Yeah, we become to a binary equation. So binary equation, basically you can use the momentum equation to get a binary equation. Also, you can get the binary equation from the energy equation, but in special case, no temperature difference. Because if no temperature difference, component for the momentum equation only include mechanical energy, then that's two equations will be the same. Okay? take a break. Then we will talk about the energy